to this talk today. Not going to talk about sea ice again. If you want to know about sea ice, I'm happy to talk about that. So this is a summary of our estimate of the sea level contribution due to Antarctica, which was published earlier this year in a special issue of Nature. And it was a collective study involving a lot of different participants, about 80 or 90 different people involved, led by the ESA CCI program and NASA as well, supported by them. But I'm going to give you a little bit of a lesson about altimetry in the middle as well, because you're here to learn something, I guess, not just to read papers. I'm sure you've all read this paper. If you like ice, please tweet about this paper. It's the second highest impact paper of 2018 at the moment. It's been beaten by a paper by Terry Hughes on coral bleaching, and he had a Netflix documentary on that. So let's try and beat them, because sea level rise is more important than coral bleaching, I'm sure. But anyway, that's a little plug. Ice and climate, I'll talk about at the start. I've added a slide because I was asked about West Antarctica. Measuring ice loss, I'll quickly skim through that. I'll try and give you a lecture on satellite altimetry, and then I'll summarize the paper at the end of it. So again, start with Earth's polar ice sheets. This is how they compare in size to the UK. I use that just because I don't want to generate more of these animations. You can pick your favorite country. It's bigger than most of them, I guess. Antarctica is much bigger than Greenland. There's about 7 meters of sea level potential in Greenland and about 57 in Antarctica. So the easy way to teach people about sea level rise is to say that's a lot of water and could cause lots of problems. And I'll show you that graphic in a moment. But that's not really the sensible way to talk about it, and I'll show you an alternative way to convince people that they should care. So this is a very simple slide about glaciology and how the Earth's hydrological cycle passes through an ice sheet and is modulated by an ice sheet. So Antarctica is millions of years old. It snowed there for a long time since the craton moved to that part of the planet. And then that snow stays on land for a long period of time. The residence time for a particle of snow or ice in the ice sheet might be 10,000 years or something like that. And so if you change the precipitation rate in Antarctica, it'll start to grow or shrink depending on that. The ice sheet loses ice in Antarctica through two main ways. Melting, a very, very small amount of Antarctica melts and runs off. Much more of Greenland does, it's further away from the pole. But most of Antarctic ice is either carved off as icebergs, drift off into the ocean, melt again, and complete the hydrological cycle. But a lot of it is melted from the underside of the floating ice shelves, which are these locations around here. And that part of the planet turns out to be important, and I'll try and give you an explanation as to why that is as we go through. So this is a cutaway of Antarctica. An altimeter will see this, fly across the Antarctic ice sheet, and it'll pass along this dotted line over West Antarctica and East Antarctica, and you'll see West Antarctica as a bump and East Antarctica as a bump, and they're above sea level, maybe about 3.5 kilometers in the case of East Antarctica. Below it is the bedrock on which the ice sits. And you can start to see now, where the ocean is, it's in light grey, that West Antarctica is sitting in this marine basin. And East Antarctica is on an island that at the moment, because its weight is depressed more or less below sea level, but if you take away the ice sheet itself, the load, that pops up. So that grew because of snow falling on land and never being evacuated enough by the glaciers. You can change the air temperature a lot, as I said yesterday, and it won't melt. You can rise sea level, and the ice sheet will just retreat to a new stable position in East Antarctica and still be insulated from the ocean at most of its location. But West Antarctica is really different. Half of its ice is below sea level already, so that we don't need to worry so much about that ice in terms of sea level rise. But we do need to be concerned because the ocean can access that ice sheet from all around it. But importantly, more importantly, the geometry of the bedrock beneath the ice sheet causes it to be unstable. So every time you retreat away some of the ice sheet retreats back to a position where the glaciers are thicker. and thicker glaciers flow faster and become more mobile. And there's an instability there, a singularity at the grounding line, which causes progressive retreat if the ice sheet is in a state of retreat, or progressive advance if it's in a state of advance. And some people might call this unstoppable. It's not unstoppable. It can be tipped back the other way if you tip the forcing back the other way. But the idea that it might be unstoppable is if the forcing is progressive, and we know that it is in parts of the planet. So what do we see in terms of sea level rise? And lots of people have told you this. Most of the ocean is rising because of thermal expansion, not a mass conservative change. The glaciers and ice caps are giving up some ice, most of it today, over the past 20, 30 years on average. Greenland a tiny amount, Antarctica a tiny amount. Why do we care? Well, we care for various reasons. The IPCC tried to predict future sea level rise based upon what we know about the components of the climate system. Lots of people have talked about this. The thing that you should pay attention to is this bit down here. Over the next 100 years, even in the last IPCC assessment, the polar ice sheets were expected to give up a very modest amount of sea level rise. And I'll come back to that, hopefully, at the very end, while you're wanting to go for lunch. Because those projections are based upon incomplete observations and incomplete understanding of the physical processes. And there are several physical processes which cause the ice sheets to be out of balance that we know about from satellite observations. So these three cartoons show you them. On the top, there's lubrication of glaciers. It's a feedback mechanism. So if I kick off, the middle it's iceberg calving, on the bottom it's ocean melting. So I kick off these animations. Some water that melts on the surface of Greenland, for example, where it melts a lot, can travel through crevasses, get to the base of the ice, and then pour out into the ocean. So that water is lost through the melting process. But at the same time, through its path through the ice sheet, it mobilizes the glacier, because the glacier flows more freely on its bed and slips into the ocean. And so that's what we call a positive feedback, because as soon as the glacier flows more quickly, it thins because it spreads out, and its surface moves then to a lower altitude where it's warmer and it melts some more. And so there's a concern that Greenland in particular could cause more ice loss in the future because of this process. Iceberg calving, or ice shelf collapse, has a force perturbation, causes a force perturbation on the glacier. So ice shelves are the fringing parts of the continent. I've talked about them a little bit. I'm not going to tell you all about glaciology here, but they buttress the grounded ice sheet, and they provide some restraining force for the glaciers that are inland. And if you remove a big chunk of ice from the front of an ice shelf or a glacier, then you reduce the forces that resist that glacier and cause it to flow more freely into the ocean, which again causes it to deflate and move to a lower altitude. But in the case of Antarctic ice shelves, we see quite an abrupt change in the flow pattern of those glaciers, and I'll come back to that in a second. Ocean melting is the biggest concern because if we warm the temperature of the ocean by a very, very small amount, 1 degree centigrade of ocean warming melts an additional 10 meters of ice per year about at the base of the continent. And the slopes of these bedrocks around the continent are nowhere near as steep as this. They're quite shallow, and that causes a big chunk of the ice to lift off the ground. And as soon as that lifts off the ground, you've reduced the traction properties of the glacier. It can flow more freely into the ocean. And so there's an indirect effect. The glacier adds more to sea level rise. We know these processes exist, but they're not very well realized within the models upon which sea level projections are based. And why does that matter? Well, this is the easy example, and it's not true. It's not going to happen anytime soon. This is part of the planet, the UK and France mainly, and this is how it would look like if we had no polar ice sheets, 70 meters of sea level rise, and lots of places would be flooded. Amsterdam might be flooded. They know how to deal with coastal defences there, but they spend a lot of money. Paris might be flooded. Leeds won't be flooded, so we'll be all right in Leeds. You can come and live in Leeds. This is not a realistic scenario in any time soon. What is a realistic scenario is what people really want to know. And West Antarctica is the realistic scenario. It's about 3.5 meters of sea level potential. How soon could the ice sheet collapse? We can look to the geological record to understand that, whether that's happened in the past, and we can appeal to models to try and understand how quickly that might happen, because unfortunately the geological record doesn't have the temporal resolution with which to pinpoint the time frame over which these changes might happen. So if we lose 3.5 meters of ice, 3,500 millimeters, in 1,000 years, it's only 3.5 millimeters a year. But if it happens in 100 years, then it's 35 millimetres per year, and it starts to become a problem for coastal protection. And why does that matter? Have you been to AGU? This is San Francisco, the Embarcadero, and that's not a real rocket, but that's a real wave spilling over onto the embankment there. And it's only a problem if it happens frequently. And in San Francisco, it doesn't really happen very frequently. This happened in 2015 at Fort Mason. The tide gauge record, well, the sea level record, spotted it. And this causes a minor disturbance if it only happens once a year or once every 3 years, for instance. What does the tide gauge, the tide height record show at Fort Mason? It shows you can see that event. It was a coincidence of a storm surge, I'm not an oceanographer, a storm surge, sea level rise, and tides causes the coastline to be flooded. What happens if you raise sea levels by 50 centimetres? Maybe that happens. Maybe it happens once every month. And then it becomes, or maybe once a week, and then it becomes an annoyance. You have to deal with that. There's a cheap way to deal with it. There's a conservative way to deal with it, and you just build a wall around the edge of San Francisco. But that might cause people not to want to visit San Francisco anymore because there's a wall around the edge of the island, and so it's no longer a tourist destination. So there's a realistic way which costs much, much more, and you either have to stop the whole planet causing sea level rise, which is not so easy, or you have to raise the whole bloody road, and that's an expensive job, and so that's why it matters. You probably know all of that anyway. But do we have any evidence that abrupt changes in climate happen? Well, we do. This is Larsen Ice Shelf in Antarctica, and it's been retreating and collapsing, I showed you this yesterday, for the past 20 or 30 years in different sections. So all of this ice has gone now, and these are ice shelves which buttress the glaciers behind them. Now, 30 years ago, before we had satellite measurements, this was an esoteric debate amongst glaciologists, theoreticians, whether or not ice shelves mattered, whether or not if you lost an ice shelf, the ice sheet would respond. And there were two camps. One set said no, it didn't matter. Another set said yes, it did matter, and they never agreed with each other. And then it collapsed, and we have a real-world experiment to establish whether or not it does matter, and it turns out that it does, and I'll come back to that in a moment. But before people could spot that with the satellite measurements, this ship, or a ship, was able to sail into the embayment that was formerly occupied by a 500-metre thick ice shelf and collect some measurements from the seabed, which is great. This is a photograph taken from the piston core on the seabed. You can see, actually, there's more than just the piston core. There's an erratic boulder there, for instance, and so if you're a real geomorphologist, you'll be interested in that, because how did that get there? It's got sharp edges, so it can't have been passed through a glacier. It must have been dropped off from the surface and travelled down the surface of the glacier. But how did it get to the floor of the seabed when there's an ice shelf there? Well, that tells us, if you can date the deposition time of that erratic boulder, when the ice shelf was last there. So you can do some really interesting things geologically, oceanographically, to try and understand Earth's past climate. This is not a story about erratics, it's a story about the piston core itself, because you can analyse the piston core and look for things in it. And you can look for organisms like this foraminifera and their abundance through the piston core, and understand when they lived in the sediments that are at the base of this ice shelf on the seafloor. And some of these organisms like to live in light environments, and some of them like to live in dark environments. And you can then understand when it was last light or last dark in this embayment. And in fact, Carol Pudsey and Jean Domack did a lot of this work straight after the collapse of the ice shelf, and they showed that the ice shelf, through dating of these sediment cores, had been there for about 7,000 years. And so this is a real-time example of abrupt climate change. It's something that hasn't happened in this glacial cycle. And does it matter? Well, Earth observation comes to help again. Drygalski Glacier, Helmut Rott and others mapped the speed of this glacier before and after the collapse event. And sure enough, this glacier speeded up after the collapse event and is now flowing about 8 times faster than it was before. So ice shelves do matter, and abrupt climate change is happening, and it causes sea level rise. And so all of these processes are qualitative in their concept, and not quantitative in terms of their incorporation into climate models that predict future sea level rise. And so that becomes a problem, because we need to trust those models if we're to invest lots and lots of money in coastal protection. And so there's a real challenge to improve the robustness of sea level projections, particularly these these components, these elements that were previously considered to be extreme possibilities, because actually they're real. We see that there are abrupt changes in climate. So there are several ways to measure ice loss. You can measure the change in shape of a lump of ice, and this is a lump of ice changing its shape, being measured. You can measure the change in the speed of a lump of ice, and this is a piece of ice, and it's being measured at speed. And you can measure the change in weight. And we have 3 satellite techniques which can tell us something about all of those things. We use satellite altimetry. We use the mass budget method, which is part satellite and part observational. The satellite gives us the ice flow, which then tells us about the ice discharge. And we use gravimetry, which weighs the planet. I told you about this yesterday. So here's the cartoon. Here's Grace, measured a piece of ice. Part of it's below sea level, part of it's above sea level. So it's all physically consistent. If the ice changes, the satellites move out a little bit. And so we measure the blue line separation of the Grace satellites in space, and you infer the weight change that has occurred beneath those sensors. And then you locate it on planet Earth and you say, well, is it down to the bedrock, is it down to the solid ice, or is it down to the snowfall? And that's where we interpret the measurement. It's as much as you're going to get from me today on Grace, because I like altimetry. Glacial isostatic adjustment, snowfall, and ice runoff all have to be taken into account, and we get those from models. So nothing is just from satellite observations, I'm afraid. And this is that animation of Grace data from yesterday, and it's going so slowly again. The Grace people need to speed up their animations, that's what I'll say. Mass budget method uses conventionally interferometry, but we now know that you can track the speed of ice with lots and lots of different satellite sensors. Optical measurements are just as good when it's sunny and when it's not cloudy. But they're just as good because ice actually moves quite quickly in terms of the Earth system. If you were looking at tectonic activity of 1 millimeter per year, you could only use interferometry. But if you're looking at ice that's moving at 15 kilometers a year, you can see it in photographs. But anyway, this is the schematic that I produced a few years ago for interferometry. Satellite, it needs to be repeat pass. There needs to be a time interval in between the acquisitions. And so separately, the satellite might return to a different place in space and capture an image of the location on the ground, same location on the ground, and there'll be a geometrical signal in there, mixed in there, because the satellite's looking from a different vantage point. So if you remember back to that fringe pattern I showed yesterday of Rutherford Glacier, some of the fringes are related to the terrain because of this effect. But if the ice moves, an additional range change due to the displacement of the glacier, and we can calculate the motion term as well separately. And we can do that in several different ways. If we have an external elevation model, or we have 2 interferograms, we can difference them to cancel out one of the signals, either terrain or motion. The motion might be associated with lateral flow of the ice, or vertical motion of tides, for instance, of floating ice, and we decompose it into its different components. But more or less, we use the technique to measure the ice speed. And then, using the ice speed, we can calculate the ice discharge if we know how thick the glacier is. There we have to appeal to external measurements. And we can then balance that against the amount of net accumulation inland. And that's the difference between snowfall and runoff. So it requires several external fields, the ice thickness measurements, the snowfall and the runoff. And in the end, this becomes a relatively imprecise result, even though the satellite measurements of ice speed are the most precise, I would say, of the 3 different techniques that we have. It's killed off by the fact that we have to difference 2 very, very large numbers. And so what do I mean by that? Well, in Antarctica today, the ice sheet loses about 2,000 gigatons of ice through glaciers into the ocean each year, and it receives about 1,900 gigatons of snow per year. And the interesting number that we're concerned with is the difference between those 2. And so it becomes a relatively imprecise method, because we need to know each of those 2 numbers with a confidence to allow the difference to be significant. And the difference of about 100 or 150 gigatons per year is quite a demand on the surface mass balance models. But nevertheless, beautiful patterns of ice flow can be mapped, and I showed you this animation yesterday as well. And so we can do lots and lots of glaciology with these measurements, because they resolve all of the glaciological features of the ice sheet, which are not resolved in the GRACE measurements. So this lecture, this talk, is about mass balance, and so GRACE is a really powerful tool for that. But for glaciology, these are the sorts of data sets you want, really, really high resolution measurements which tell you where the ice is and how it's changing. Altimetry, by comparison, is really simple. We have a satellite in space, preferably cryosat, and it ranges to the ice sheet surface, and if the ice sheet moves at all, it measures the difference. And so it couldn't get simpler, except to convert that to mass, we have to understand, and I'm ignoring here the glacial isostatic adjustment, which is a relatively small correction to the satellite altimeter measurements, but still there. If the solid Earth moves underneath it and pushes the ice up and down, then the surface will change because of that. But it's not nearly as great a signal as it is for GRACE, which has to account for the density difference between the rock and the ice as well. But we still need to know something about the density at which the perturbation has occurred. Has it occurred because the snowfall at the surface has changed, or has it occurred because the glacier ice at the base has changed? And that becomes complicated. And there are several ways we can look at that, and I'm going to show you with white background slides to separate it out as a lecture, how we briefly do that with satellite altimetry. Because any of you that are interested in satellite altimetry, send me an email, and I'm happy to talk about it at length afterwards, because we're always keen to work with people who like altimetry. So radar altimetry with white backgrounds, really easy. This is a radar, and it's firing a wavefront at a flat surface, and you would think you should be able to range to that surface quite simply and measure the distance between the target and the surface. But the problem is the surface is flat and the radar's wavefront is spherical, and that interacts with the surface in a way that sends back energy that is not the same shape as the original transmission. So this is a really simple cartoon way of how an altimeter works, because the backscattered power is proportional to the area that's illuminated per unit time by the wavefront as it interacts with the surface. And that starts out as a growing, in plan view, a circle, but then when the back of the waveform arrives at the surface, when the echo ceases to be transmitted, it's a decreasing radius annulus, and that has a power signal that looks like this bottom echo. So we send out a transmitted pulse, which notionally might be a top hat at the in the top panel, and we receive an echo that is not the same shape. And the problem is we're trying to measure the time delay between these two things. I hope you've been taught about this in the ocean lectures as well. We're trying to measure the time delay between the two things, and the precision with which we can measure that time delay determines how precisely we can measure elevation of the Earth's surface, with some other corrections, the altitude of the satellite platform, for instance. But the two things don't look the same. And so how do you measure a common point on the transmitted pulse and the echo? And the way we do that is we look for the peak, tend to look for the peak power in the echo. But these are just idealized echoes from a cartoon that I drew several years ago. This is what a real surface looks like. You can see this as an ocean or a rough ice sheet. And as the satellite transmits its pulse of energy to the surface, we get scattering back from different locations. So the first echo comes back from the closest point that the satellite sees, down here. Sorry, you might not be able to see it from the table. So we get one echo back then, but the next one comes back here. It's lower power because it's transmitted further back in the echo. And then another one, another one, another one. And ultimately, they stack together and create a distorted waveform, which doesn't even look like this nice top hat. Over an ocean surface, which is more or less like this, it's really well behaved, and you can easily spot that peak. And so ocean altimetry, it's easy. It's really easy because it's a really precise measurement. You can't fail to spot that peak. But it doesn't work like that with ice sheets, unfortunately. So there's your ocean echo, typical ocean echo, very, very peaked, very easy to locate that peak. But this might be an ice shelf echo, where the surface is rougher. So the width of the leading edge, the front end of that waveform, which is this point here, it tends to be related to the surface roughness, and this is how we calculate significant wave height, for example, over the oceans. The rougher the surface, the broader the width of that leading edge of the echo. So this is how we calculate interesting parameters, retrievals from satellite altimeter echoes, other than just the range to the target. But the trailing edge of that echo still contains power. And that's because of the scattering that happens at successive travel delay times as the radar waveform penetrates into the ice. And over in the interior of the ice sheet, it's even worse. The width of the leading edge is very, very broad because the surface is very, very rough. This instrument wasn't designed to look at an ice sheet surface, but we still use it. And there's a great degree of penetration into the snowpack, and so it becomes a very, very diffuse echo. And it's much, much harder when if I were to add the actual speckle noise that we get on radar echoes to them, it's harder to locate the peak. And that reduces the precision with which we can measure elevation. So there's lots and lots of work, PhDs, on looking at individual altimeter echoes and trying to improve the way we might measure simply the height of the Earth's surface, let alone interesting things, as if the height of the Earth's surface wasn't interesting, about the glaciology of the targets like this that we're looking at. So very, very briefly, to calculate elevation change, we tend to rely on the fact, well, we do rely on the fact that satellite orbits repeat in time. And this is a repeat pattern of ISAT. I use it because its orbital pattern was compromised because of the mission, but that at least allows you to see the crisscross pattern of its orbits. When you zoom in to a classic mission, this is Cryosat, in 5-kilometer grid cells, you can see that crisscross pattern, more or less, and there's some echoes which come from further off nadir. And then this is the resolution with which we want to measure. Well, if you ask people what spatial resolution you would like your satellite measurements, and they'll say maximum. And so that's not usually a helpful requirement. But at 5-kilometer resolution, most grid cells are populated with information. And so we take that as being the native resolution at which we might be able to produce a useful product and try and devise ways with which you can measure elevation changes over a time period. The classic method I talked about briefly yesterday is to use simply the crossing point locations where we can cancel out the terrain slope. That's really useful because it becomes really precise, but it throws away lots and lots of data. So that's using just these data here, the red data here in this crossing point location, and the same red data here and here, and it throws away all the information along the satellite's orbits. So we can do better, and some people, Frederic Remy and others, invented a technique where we can collect the measurements along the satellite track, and there are various approaches to measure elevation changes by accounting for the surface slope and the drift of the satellite tracks relative to one another along track. And so these are two classic ways, lots and lots of work going on to try and improve the method itself of relocating the satellite echoes in space on the ground in the first instance, and then accounting for residual slope effects, which are all limiting the precision with which we can measure elevation. What can you do if you are careful with all those measurements? You can generate these sort of time series of elevation change, 25 years or so, of the ice sheet, and show the pattern of deflation emerging, particularly here in West Antarctica, over that 25-year time period. And if you look carefully, there are other signals as well. There's a deflation here in Totten Glacier in East Antarctica, and there's an inflation here. And there's glaciology in all of these signals. It's not just about the sea level contribution due to the ice sheets. This is a 5-kilometer product across a 5,000-kilometer ice sheets. You could spend a lifetime looking at your own favorite glacier, and these measurements would tell you more about the glacier than you knew from field measurements alone. How do we convert to mass? This is the biggest bone of contention for satellite altimetry because it's becoming clearer and clearer that we need to take into account the surface elevation changes due to snowfall and melting. So on the left-hand side is the pattern of elevation change that I just showed in that previous plot, but now scaled between plus or minus 10 centimeters a year, so saturated out. You can see areas in blue are deflating, areas in red are inflating. And on the right-hand side is the model realization of elevation change just from surface mass fluctuations alone. So that's snowfall or ice melting. And you can see there are lots of similarities between those two signals in many places. So in East Antarctica, this part of the ice sheet over onto the right-hand side here, more or less, the surface firn model, firn compaction, is telling us about all of the signals we see in the surface altimetry. But then when we look to West Antarctica, it's not the case. So this signal here is the very obvious one. Very, very bright red inflation here. No signal of inflation at all in the firn model. And that's because this is an ice stream, a collection of ice streams in East Antarctica, in West Antarctica, should I say, at the Saipan coast, where incidentally the Americans spent the first 30 years of their modern-day field program investigating. because they thought it might be an area of potential ice sheet collapse. Turns out exactly the opposite is happening there. The glaciers have slowed down, and because they slowed down, the ice sheet is inflating. They stopped to move. For some reason, the basal properties of the ice have grabbed the glaciers onto the seabed, and the ice is banking up behind them, and that's inflating. It's got nothing to do with surface mass processes at all. It's all to do with glaciers, which is the difference between these two fields. But very similar to the input-output or mass budget method I talked about before, if you want to absolutely correct for the change in elevation associated with snowfall, first of all, you have to be very confident that that Föhn elevation model is correct. And this is an area where global climate models weather models perform very, very poorly in the polar regions. And these are just nested grid weather models run in Antarctica and Greenland. But also, the altimeter time series that we have here on the left-hand side is built from radar measurements. And the radar measurements don't see the actual surface elevation change. They see the elevation change of the scattering horizon and not the actual true surface, which is what's being modeled here by the Föhn elevation data. If we had a laser altimeter time series, it should see exactly that signal on the right-hand side, but we don't. We have a radar time series, and if the Föhn pack is warming, then the scattering horizon is going to migrate upwards. And so today, we still don't have the perfect situation where we can difference a Föhn model and a radar altimeter time series to correct for the snowfall fluctuation. So we have to do something else instead, which is a very unsatisfactory approach, I have to say. We take the signals identified as being in a dynamic imbalance, popping out of the satellite measurements themselves, and we assign a density of ice to those. And that's a real problem because it's a one-dimensional model, and it doesn't allow for contemporaneous elevation changes associated with dynamical thinning of the ice and surface mass balance processes. So if you've got a better idea, suggest it, apply it, and take all the glory. So ice sheet mass balance. Satellite altimetry, you know a little bit how to do it with satellite altimetry, and in a cartoon sense from the other two techniques. Have people done this in the past? They have. So this is for Greenland, estimates of ice sheet mass balance in the published literature. So there are four essential techniques, radar and laser altimetry, separated out for some reason or other. And this is the first estimate of ice sheet mass balance published by Jays Wally for Antarctica, for Greenland, should I say. Or maybe this is Antarctica, we'll see. I think it's Greenland, as you can see, Jay estimated the rate of mass change over about a 10-year time period. And his estimate was very, very precise because the vertical range of this block is the error bar. And so he estimated the ice sheet mass loss within a fraction of a millimetre per year. And then somebody else came along, and that was the first estimate, and published another one, which was also very, very precise, over a very slightly different time period, and didn't agree with the first one. And so this is where the confusion starts. Here's another one, laser altimetry, here's another one, here's another one. And it was a big business back in the day. Lots of people making their own estimates of the ice sheet sea level contribution, 41 in this example. And the problem is that most people don't care at all about the ice sheet at sea level contribution, except they just want to know the number. And so we invented this project IMBY to try and collate all these measurements together. One of the things that you can see very strikingly from here is the problem of introducing a satellite method at a late time period. So the GRACE data here, the gravimetry data, not only do they not agree with each other because of the various geophysical corrections that people are applying, but they differently. But they're all weighted over to the right-hand side. And so is that a real change in the rate of ice loss from Greenland, or is it a systematic issue with the satellite measurement techniques themselves? And so we invented this project that did several things, very, very simple things, to try and improve confidence in those methods. First of all, we got lots and lots of different people involved, and there are more now. But secondly, and quite importantly, in fact, we just said, well, this is the map of Greenland, and this is the map of Antarctica, and its subset ice sheets, and you have to calculate your measurements over these areas. And it's surprising how different the answer is if you use just a very small area change for the two ice sheets. And then we also said, please use the same time period as a comparison technique, so that we can compare apples with apples and not apples with oranges. And that first paper was very well received. It lends confidence in the sea level measurements, sea level ice loss measurements themselves, which is really important because before then there were periodic arguments in the literature about what the number was from different groups, and that's not helpful. It's a bad sign that different techniques potentially disagree with one another, and it's a bad sign that a community is at odds with one another, and that's not a good message to send out because the rest of the climate science community are not interested in your own individual squabbles. And actually, when you force people to say, let's compare things properly and equivalently, then they can no longer say that my technique is better than yours, it's just an alternative. So what's happened since then? Unfortunately, people still publish estimates of sea level rise from their own methods. So this was the state of affairs in 2012, and we have now the 50 estimates for Greenland. But you can see there's a progressive trend emerging now here for Greenland. And Antarctica the same. We have another 30 or so estimates. But there's a problem there. You can see that Antarctica, the spread seems to be diverging quite a lot, and that's among the GRACE solutions. And one of the key things that we did this time around in the IMBY assessment was to pay particular attention to the glacial isostatic adjustment models that were being used to correct the GRACE measurements. And we have a particular experiment group which is designed to try and understand which of those are realistic, because they are external model fields and they can cause big variations in the rate of mass loss of the ice sheet if you're attributing that signal to rock instead of ice. So this time around, we had many more satellite missions. We used to have 10 different satellites. We now, well, I think we have more than 13. We have a lot more satellite data, which is great. That's a good motive. We have 5 key experiment groups. If you're interested in any of these techniques, talk to your experiment group leader. And we have people from lots of different countries around the planet, not just ESA and NASA member states. We have participants submitting data for Antarctic Peninsula, East Antarctica and West Antarctica using the 3 different satellite techniques. We have lots and lots of data. It's a completely open exercise this time round. Anybody is allowed to participate. These are their individual data sets. So these are now rates of mass change for the different ice sheets from different people from the different techniques in vertical columns here. I won't dwell too much on this other than to say in most areas the techniques are more or less on top of each other, but there are some obvious departures. Here's one. You can see one here. This data seems to be fairly static with a gap in between and at odds with the rest of the measurements themselves. And in the Antarctic Peninsula, in particular, the GRACE measurements are starting to diverge from one another. And this is because here there are different theories as to what's happening to the geological the geology beneath the ice sheet, and there are evolving ideas as to how the glacial isostatic adjustment is responding in that part of the planet, and people use different GIA models. And so there is still room to understand the differences between the techniques themselves. We think we understand why people have results that are diverging from one another, but that is beyond the scope of this exercise these days. When we collate the results in common areas, we can calculate the rate of mass loss, integrate the measurements up first to within their respective satellite techniques, altimetry, gravimetry, and the input-output method, mass budget. And the consolidated estimate in grey overlaps all of the individual estimates. But that hides some of the bias that still exists within the techniques. And so, more or less, the altimetry results are always more positive than the mean, except for in East Antarctica. And more or less, well, everywhere, in fact, the mass budget or input-output method are more negative than the mean. And so there are biases in the respective techniques which need to be ironed out. The GRACE data tend to fall at the mean, but that's not to say that GRACE is right and the other two are outliers. Nobody knows the real answer. And so there's scope to improve confidence still in the respective satellite techniques. Which one is the best for measuring ice sheet mass changes? And the jury's still out on that one. And it's going to require more work on the individual techniques themselves to iron that out. So when we collect all of the measurements together, this is now for West Antarctica, over a full time period. This is just over the common time period at which the techniques are available. This is the pattern of ice loss. The rate of ice loss from West Antarctica on the left-hand side in gigatons per year, on the right-hand side as the equivalent sea level contribution. In the 1990s, the ice sheet in West Antarctica was close to a state of balance and now is quite far out of balance by most, in fact, all measures. On this plot, which is inverted because I like the black slides, the measurements themselves are color-coded, and the 1, 2, and 3 sigma uncertainties on the central estimates are shaded in different shades of grey. And what we find is that all of the estimates fall within 3 sigma, and the vast majority fall within 1 sigma of the individual results. Same pattern for the Antarctic Peninsula, same pattern for East Antarctica. The Antarctic Peninsula is a very small area, but it's glaciologically interesting because it's far north and it experiences different climate processes there than the rest of the ice sheet does. First, in terms of the forcing, it melts there a lot more, but also because of the events that have happened, this is where the ice shelves have collapsed. And so we separate it out, but it's actually the toughest thing to measure because it's quite small. It's 4% of the Antarctic continental area. But it's responsible for 25% of the ice loss. And it's very, very rugged terrain. It's a mountain chain with ice sat on top of it. And so it's a challenge for all of the satellite techniques, but nevertheless, we still produce an estimate there. It's the least certain in terms of the individual measurements. And East Antarctica remains a problem. Over the 25-year time period, the ice sheet overall hasn't changed in mass, but there's a big error bar, not big relative to the size of the ice sheet, but a big error bar nevertheless on those data. If you integrate them up over time, you can see the sea level, the total mass change of the 3 ice sheets, and there's the number, 3 trillion tons in total has been lost from the Antarctic continent as a consequence of the processes that I've just talked about, mainly happening in West Antarctica and at the Antarctic Peninsula over the past 25 years. And there's a curvature to that trend now that wasn't apparent the last time we looked at it, and I'll come back to that in a minute. So we carve up the measurements into 5-year intervals, and you can see in Antarctica as a whole a progressive increase in the rate of ice loss over the past 10 or 15 years. So now the ice sheet in the last 5 years is losing 219 gigatons of ice per year, whereas in the 1990s it was only losing 50 gigatons a year. So 5 or 6 times the rate it was in the 1990s, and 3 times the rate it was prior to 2010 when we last performed this assessment. As I mentioned, we have 2 other experiment groups, one looking at the surface mass balance data. These are all model results. Michiel van der Broek is running this experiment. And he analysed surface mass balance model estimates of the total mass input to the ice sheet. And depending on which model you use, you can range from, as low as 1,800 gigatons per year to as much as 2,150 gigatons per year. And that's important because there's a difference of 350 gigatons per year in the surface mass balance models alone. And so that variance among those models might be taken as a measure of their confidence. And so if we're trying to detect 200 gigatons per year mass loss, the mass budget method is probably the least reliable way of doing that because the variance in between the surface mass balance models is more than twice the rate of mass loss in and of itself. And that's not even looking at the uncertainty in the satellite measurements of ice discharge. So while the ice discharge measurements are really, really powerful for telling us why the ice sheet is losing mass, because they're the ones that measure directly the glaciers, they're the least reliable in terms of integrating the total mass change because they depend upon weather models, and the weather models show a lot of variance today. And so there needs to be improvement in that measurement. But they would come back to us and say, well, a 10 or 20% accuracy of our measurement technique, that's good enough, right? But it's not for the mass budget method. And then glacial isostatic adjustment, which affects predominantly GRACE, but also altimetry, this is a problem as well. These are 11 different GIA models across Antarctica. One of them puts the GIA signal at 80 gigatons per year, and another one puts it at 10 gigatons per year. So there's 70 gigatons per year variance among the GIA models, and yet that uncertainty isn't present in any of the GRACE estimates of total mass loss from the continent. And so this needs to be addressed as well. What is the glacial isostatic adjustment of Antarctica? And how do you do that? You drive around Antarctica or fly around Antarctica and put GPS out on mountain tops. It's really nice to do one of those. It's not so nice to do 50 of those, and especially to go and dig them out again next year to measure their signal, to download their signal. I was with a colleague that was doing that this January in Antarctica. He had to dig through 3 meters of ice to get to his seismic meter. So, what can we interpret about the elevation changes? This is a map of the surface elevation change of the continent in fine spatial resolution now over the 25-year time period. Yellow is signal that shows no change, blue is thickening, and red is thinning. It's the same signal that you've seen in the other plots. But now on the outside, in the ocean, is the average ocean temperature at the depth at which the glaciers touch the ocean. And you can see now that the areas of ice loss are abutting an ocean that is too warm. That's where the ocean is at its warmest. Now, the problem we have today in oceanography is that we don't have a long time series of ocean temperature measurements, so we don't know what the forcing is and how that's changed over time. And this is important because if this could be a stable state, the ocean could be a stable state, it has to be an anomaly in order to be out of balance with the ice sheet. So the implication is that this is an ocean anomaly. Whether or not that's associated with the global pattern of change or not is not clear. But if you look at the magnitudes of the ocean temperatures, all of the ice loss, or 90% of the ice loss from Antarctica, has occurred in the Amundsen Sea, where the ocean is 0.5 degree centigrade warmer than it needs to be. And that's a really small amount of heat, you might think. It's consistent with the planetary average temperature increase, for instance. But it's enough to unground the glaciers at their terminus and cause them to be unstable over a decadal time period and worry us about future sea level rise. This is a cartoon of what's happening. I'm just showing you this to illustrate the wonderful things that the Nature Art Desk do. So they asked me for a cartoon of the process, and I drew this, and they turned it into that, which was nice. And so they do all the graphics for you. And there are lots and lots of interacting processes. So it's even the case that the sea ice and the brine rejection that is associated with sea ice formation causes a disturbance to the salinity profiles that are entrained within the plumes that flow beneath these ice shelves. So it's a very, very interconnected system. What's going on in Antarctica is really obvious. The glaciers are speeding up and they're melting, but what's causing it is not so obvious. It's not clear what's caused the warm water to intrude onto the continental shelf. It's not clear whether that's associated with a readjustment of an ocean current or a general regional ocean warming. What's certain is that that water that's present beneath these ice shelves is melting them away, causing ungrounding. The grounding line retreats, the glacier lifts off the seabed, it reduces the rate of friction, and it speeds up and then thins and pours more ice into the ocean. So that side of the equation is really clear. The right-hand side is definitely not clear, and it's an unsolved problem in climate science, whether or not the signal of imbalance in West Antarctica is related to anthropogenic global warming. What does it mean for sea level rise? Well, turn those numbers from gigatons a year into millimeters or total millimeters. So over 25 years, oh, that's a shame. The Antarctic ice sheet as a whole has given up about 8 millimeters of sea level rise. So that's not a big number. Is it something that we need to be concerned about? Well, the answer is yes. But let's go back in time a little bit to IPCC projections, because we've done this. In the last 5 or 6 IPCC reports, they've all made sea level projections based upon some global climate model or a concept of a global climate model. In the first IPCC assessment report, well, this is, for comparison, the sea level contribution due to the satellite observations. So this is Greenland and Antarctica. Most of contemporary sea level contribution is due to Greenland, and some of it's due to Antarctica as well. At the time of the first assessment report in 1990, now 20 years ago, more or less, the Greenland ice sheet was understood to lose ice in a warming climate. This is predictions that have actually now happened. So in 1990, predictions were made for this period that we've lived through. Greenland was understood to contribute sea level rise because it was known it would melt at the surface. But Antarctica was thought to grow because the only process that was included was increased precipitation associated with more evaporation from the oceans, which causes an ice sheet on its own to grow because it takes longer for that snow to come out. So Antarctica was expected to grow because the models then didn't include glacier processes. In fact, the models then were a linear equation relating ice gain to temperature across the planet, which is a very, very simple model. You can't get away with that as a climate model today. But in AR2, it was the same situation. In fact, Greenland was expected to lose a little bit less ice. The models have got more and more sophisticated as time goes on until we get to today. But the Antarctic's contribution was still expected to be net growth, the same in AR3, the same in AR4. But in AR5, we started to incorporate dynamical processes. And that's the first time that at least the sign, but also more or less the magnitude of the predictions start to match the satellite observations. So the power of the satellite measurements isn't just in telling us what's happened today, it's in giving confidence in the models upon which future predictions might be based. So how does the measurement that we published in June, I think, stack up against the sea level predictions from AR5? Well, that's the total sea level contribution due to Antarctica. As I said, in the early 1990s, it was contributing about 0.2 millimeters per year to sea level rise. And then in the last 5 years, that's tripled. And so that's a concern. That was the main headline for the paper. This is the AR5 prediction over the same time period. Unfortunately, they started the AR5 predictions in about 2005-6, and so let's try and start the AR6 predictions at the beginning of the satellite record, because that gives us a little bit more time to match them up. But the lower range prediction and the mid-range prediction and the upper range prediction from the AR5 models are quite different to one another, and they're not different because of the scenarios in terms of the emissions. They're different because of the processes that are incorporated in those models. And so the lower end predictions were excluding ice dynamical processes, because it wasn't clear, there wasn't a consensus in the literature that these would actually take place. Well, when we had only data up to 2010, in fact, Antarctica was tracking this lower range of predictions. But you can see now clearly we're tracking somewhere, the ice sheet is tracking somewhere between the mid and upper range of sea level predictions from AR5. What does that mean into the future? Well, this is now on a centennials timescale, font problem at the bottom, but that goes up to 2090. This is the satellite record now, and you have to believe that the satellite record is useful over a 25-year time period, but century scale, this is a small number. Well, here's what the models do. So AR5 lower sea level prediction was meant to reverse and cause mass gain for Antarctica, again, over a centennial timescale, because the glacier imbalance was going to be offset by snowfall gains. The mid-range prediction allowed for 5 centimeters of sea level rise over the next century, and the upper range is 15. And the fact that so the difference between the upper and the lower range is more than 20 centimeters of sea level rise. Well, if you go back to the storm surge information that I gave you earlier on, that's enough to increase the frequency of flooding in coastal areas by a factor 5 to 10, the periodicity of that. And so those numbers really do become important for town planning on centennial timescales. So to summarize the exercise, now lots and lots of people involved in it, lots and lots of data sets contributed. We're looking hard at the GIA and surface mass balance models to try and improve the way we use them and the way we feed back to their creators what we require of them. And the sea level contribution for Antarctica has increased. It's tripled over the past 5 or 10 years. We're tracking the upper scenario for sea level predictions, and the contribution, the losses are dominated by West Antarctica, but we see a sniff of an increase at the Antarctic Peninsula too. East Antarctica remains a challenging area for us, and the mass budget method is the least certain and also the most negative. So there are things we can look towards the future. There are more satellites, so we hope to incorporate Sentinel-3, Grace Follow-on, ISAT-2 and NISA. We're going to report soon on Greenland as a separate paper. We are going to incorporate the conclusions from the surface mass balance and glacial isostatic adjustment groups into the satellite, the respin of the satellite measurements the next time we do it, because the aim is to produce annual assessments. There's no reason why we should wait 5 years between measurements of the global sea level contribution due to the polar ice sheets. It should be a data set that's available to hand, perhaps not on a monthly basis, but certainly on an annual basis. And that's something that's hard to work towards, because actually this was an unfunded project for most of the participants. So this is just a community assessment. The The benefits of the data will come in their ability to challenge the numerical models now that are being run as part of the AR6, the CMIP models, and that's being done. So we're involved in the ISMIP6 activity, which is the ice sheet modeling to comparison project within CMIP. So these measurements are being used to refine the predictions from the next generation of models. So let's hope that the data feature within AR6. And it would be nice to incorporate glaciers as well, but they're a much more challenging target to survey from space. That's quite a lot, I appreciate. What do I want you to think about? Well, satellite measurements are really, really powerful for glaciology and for climate science. They can tell us important numbers that people are interested in, for sure, the sea level contribution due to the polar ice sheets, but they can give people confidence in the model predictions. And that's, in the end, where politicians sit, because they need to be persuaded that the predictions for the future are confident enough for them to invest money to build a sea level protection around San Francisco, for instance. But you have to take it to the local level to get action, unfortunately. So you need to look, that was just a very casual look at the tide station records around San Francisco, and you could do that for any regional city, and regional sea level rise will be the concern for the future, for sure. It's not the mean global sea level. So I can say ice losses in Antarctica cause sea levels to rise preferentially in the northern hemisphere, and the converse is true for Greenland, just because of the gravitational redistribution of mass. But a 20% increase in mean sea level in the northern hemisphere is nowhere near as important as perhaps doubling on the eastern seaboard of the USA compared to the west, for instance. So regional sea level forecasts will be the important goal for the future, and downscaling the satellite measurements of ice loss and what they mean for coastal areas is a really important challenge. But also, in amongst all of that, I tried to give you a little bit of lecture about how the satellite techniques themselves work, because it's not about just telling a story as a geographer to people and explaining to people in plain language why this is important and what you've found out. But it's actually at the back end, it's me and other people sat behind computers inventing ways to manipulate the satellite measurements themselves and do better than when we were expecting 30 or 40 years ago. So don't use the waveform retracker that was coded up in 1960 to measure ice sheet elevation changes. Just because it's in the satellite product that's being distributed by the space agency doesn't mean that's the one that you need to use. You can do better than this, and that's the exploratory nature of Earth observation research. So you've got 2 or 3 minutes before lunch. Thank you.
Thanks for that. Are there any questions? Okay. Sorry, I didn't see who was first.
Hi, thanks for the talk. I'm not sure if this is a stupid question or not, but has anyone discussed how to validate the satellite altimetry measurements?
Well, no question's a stupid question, right? That's why the space shuttle crashed, because it was expected, like the chance of a space shuttle explosion was 1 in 10 to the 4, and actually ended up being 1 in 10 to the 2. So no such thing as a stupid question. We do validate the measurements. For satellite altimetry, there's a range of sources, but we tend to rely preferentially on airborne altimetry. And there are lots and lots of airborne laser campaigns around Antarctica now, thanks, in fact, to the failure of ICESat. They didn't exist before ICESat, but NASA spent $10 to $20 million per year flying airborne campaigns as a bridge between ICESat 1 and ICESat 2. And they never expected it to take them a decade, or 15 years in the end, when they burnt through the best part of $300 million flying airborne campaigns around the polar ice sheets, which is the price of 2 cryosats, for example. But nevertheless, they did that. And actually, for us, it's really, really powerful data set now, because it gives us independent measurements of the same signals that the satellites see, but much more precise, because the navigation and the range precision of the sensors is far, far better. So we use those in the main.
Cool, thanks.
You mentioned that surface roughness can affect the confidence in your altimetry measurements.
Yeah.
So if you had like discoloration of the ice surface due to pollution or something, would that mean you would not trust your altimetry measurements as much, or you'd have increased uncertainty?
So most of the electromagnetic scattering experiments that have been done on snow and ice were done by the US Cold Regions Research Laboratory, CREL, about 20 or 30 years ago. And it's really, really hard to get modern day experiments done under the same conditions because they're quite expensive. So we have to appeal to those experiments for most of our understanding of how radar waves interact with different types of snow. But what I would say is if you had some perturbation like, I know, colour or carbon deposits, for instance, which we've seen, they fly around the planet on the ice, that's going to change the physical properties, the rheology of the ice, because it will promote melting. As soon as you darken the ice, it promotes locally melting, and that will change the rate at which the water percolates through the firn pack, and that changes the crystalline structure within the firn pack itself. And if you go and dig in Greenland in areas where even if you've got algal blooms on the ice sheet surface, you see this red snow in places. It has an effect on the stratigraphy that you see within the ice column, and that has a very, very big effect on the integrated scattering properties of that column. And so, yes, I would expect it to influence things. And it's really problematic. So I like to talk about Antarctica because we have a lot less of that going on. If you dig through Antarctic fern, and that's somewhere between snow and ice, you can carry on digging and digging in most places and you'll never hit a layer at all. The only way you see layers in Antarctic ice is through the geochemistry, really, really fine chemical deposition that changes seasonally around the planet. And that doesn't seem to affect the radar because the wavelength of the radars that we use, Ku band, is much larger than the chemical properties can disturb. But if they promote additional physical changes, which they can in warmer climates, then they do definitely have an effect on the radar signal.
So what do you think about the Cantor and polar hydrofracturing mechanism? Do you think it could really happen in the future?
Do you mean the ice cliff
The
or
hydrofracturing?
hydrofracture?
Yes.
So so ice shelves at the Antarctic Peninsula have been collapsing. I showed you the examples. And I wrote a paper a while ago which said that the collapse of Larsen Ice Shelf, that the Larsen Ice Shelf was melting at its base. And so we had some satellite measurements which showed that it was thinning due to basal melting. And we ran a numerical model then of the ice shelf, and we found that if you melt it, surprisingly enough, there are crevasses on the base of these ice shelves as well. So just as much as you get at the surface, crevassing because of the spreading out of the ice onto the sea surface, you get crevasses at the base. And so there's been a strong argument about these surface crevasses filling with meltwater and that being prized apart. But the basal crevasses are already full of water and being prized apart. And the ice shelf is fractured all the way to the sea surface at its base, which is 9/10 of the thickness of the ice. So I still believe that the main destabilization process for ice shelves in Antarctica is changes in the ocean conditions and not at the surface. Just because physically, that's where 90% of the thing is cracked through, not at the surface. But there is a link between aggressive melting at the surface and water ponding in crevasses. No one's ever taken a photograph of a crevasse full of water.
But that would mean that the 1 meter projection from these others is probably unrealistic.
That's not so. There's the extreme sea level projection of 1 meter by the next century comes from ice cliff
from Antarctica
failure.
alone.
That comes from ice cliff failure, and that's a different process. But
it's what I was.
Okay, so the ice cliff failure. This is De Cantor and Pollard, and they've come up with a concept where a glacier, as it flows into the ocean, it is preferentially melted at the base of the glacier, and that causes it to tilt because it's losing mass at its base, and it can theoretically cause the cliff to fall forwards and snap off. And the promotion of melting at the base in a warming climate can theoretically promote faster and more rapid cliff failure, which can then cause perturbations to the glaciers inland. It's never been witnessed in reality. It's a theoretical concept.
Yes,
and so I would stick to known glaciological processes for the time being, because there are enough problems of incorporating the processes which we know are happening today into ice dynamical models, let alone delving into the realms of fantasy. It's not a new theory. Unfortunately, that the ice cliff failure theory was first proposed in around 1970. Look for papers by Mercer and Kees van der Veen. You'll read it then. It's just that there was nowhere near this level of sophistication for the ice dynamical models to realize that process back in 1970, because I suspect models in 1970 were made of plasticine and not numbers.
Okay.